just beats once. And so that's what a particle is in quantum physics, is essentially a constructive interference of similar frequency waves that produces a high amplitude in one region and a low amplitude elsewhere. So there are incredibly interesting applications to this idea of beat frequency, and we'll explore more of them for those of you that go on to Physics 2HC. Any questions about that? Okay, next I wanted to talk about the Doppler effect. Okay. Now, with the Doppler effect, we have a change in the pitch, but it's not an absolute change in the frequency. It's just a perceived change in the frequency due to relative motion between the source and the observer. So anyone that's gotten a speeding ticket from a radar gun knows what I'm talking about. Okay, what's happening there is that there's a certain beam of radiation, microwave radiation, that comes out from the radar gun, bounces off of the moving source, that changes the frequency, comes back to the receiver, and that receiver then has a different frequency from the frequency that came out, does a little mathematical calculation, which we'll do here, to calculate the velocity. And then he writes you out. Also, the Doppler effect can be used to measure the speed of receding galaxies, because typical galaxies are moving away from us at ever-increasing speeds as they get farther away. So there's a shift in the color of the light that comes from these galaxies. And from that, this is one of our main ways of verifying that the Big Bang occurred, is that the galaxies are moving away from us at ever-increasing speeds. And the ones that are farthest away are getting the biggest speeding tickets because they're moving away the fastest. So by working the cosmic movie backward, we can estimate when all of these galaxies were pretty much in the same place, about 13.7 billion years ago or so. There's a little bit of third significant figure is still being debated a little bit, but it's somewhere, we think, between 13.5 and 14 billion years old. Okay, so let's do this for sound then. And so we'll define the Doppler effect then as being the apparent, underline that word, shift in frequency due to relative motion between the source and the observer. Okay, and so an example of this then with sound is just a train moving toward you. You might hear a higher pitch sound as it moves towards you, like this, and then it drops in pitch as it moves away from you. But is the engineer changing the pitch of the engine for your benefit? No. This obviously must have something to do with the relative motion between the train and you. So you hear the higher pitch when it's moving toward you, the lower pitch when it's moving away. And so let's look at two different ways we can get a Doppler effect. Case one is moving listener or observer, fixed source. Okay? And so what's going to happen then as the policeman moves toward this guy, is that we have to add together the velocity of the wave with the velocity of the observer here, the listener. Okay, and so what that does then is that increases the frequency. So frequency times wavelength equals wave velocity. And so in this case then, as you move toward the observer, the relative velocity increases. Right? It's like if two cars are moving toward each other and each one is going 60 miles an hour, the relative velocity is equivalent to one of the cars being stationary and the other one going 120. There's a relative velocity. That's the sum of the two, basically, here. And so we have the velocity, I'll call it velocity of the observer, VO, plus the velocity of sound here for, well, let's call that V, for the speed at which the wave energy is moving away. But we see here that the wavelength isn't changing. The wavelength of the sound doesn't depend on the speed of the observer. And so this stays constant. So if the relative velocity goes up but the wavelength stays constant, that means we get an increase in the frequency for relative motion toward. But if the policeman started moving in the opposite direction, the guy gives him $100 not to give him a ticket, so he turns around and goes in the other direction. Then the relative velocity would be less and the frequency would drop. So that we have a decrease in frequency. For relative motion away. So this is case one. Fixed source, moving observer. Let's go to case two. In case two, and let's not worry about the policeman moving now. Let's say the policeman is stopped, so we don't have to worry about both motions at the same time. But now, this guy goes, I'm getting out of here. And so as he moves, notice that the wavelength is shortened on the near side and is lengthened on the far side. Why? Because in the amount of time that it takes to produce one cycle of the wave, you've moved this distance, and that distance is equal to the velocity of the source times the period of the wave. And so we see what's happening here then is that because of this effect, it's not the velocity of sound that's being affected, because the velocity of sound is still moving toward the fixed observer. But what's being changed here is the wavelength. The wavelength is decreasing. So for this is case one, case two. Frequency times wavelength equals wave velocity. So in this case then, for motion toward, the wavelength gets smaller. So if you're over here, you're moving in this direction, the wavelength is shorter. So then the frequency then becomes the velocity divided by a smaller number, because this is smaller this is bigger. So for relative motion toward this listener, because the wavelength is smaller, but the velocity is the same. The speed of sound is still the same value, and there's no relative motion between the observer and the sound. It's the wavelength that's become the determining factor for how the frequency is changed. And so if the wavelength is bigger, that's motion away. So that's what the policeman, if the policeman's not moving here, seeing a bigger wavelength, and so that's going to be a lower pitched sound. So that means the frequency is lower. So we can say then that in general, for either a case 1 or a case 2 situation, the relative motion of the objects, if it's toward, the frequency goes up. For either case 1 or case 2. And for relative motion away, the frequency goes down. But for two different reasons. One, in this case, is a velocity change for the fixed source moving observer. In the other case, it's due to a motion of the source creating a change in the wavelength. Now, I could ask you conceptual questions that relate to those things that wouldn't involve a lot of math. I can go through all the derivations of these things. They're in the book, though, and what I'm going to do instead is just write the final result and show you how to work with this result. So this works for both things happening at once. F prime, this is our Doppler shifted frequency. It's equal to F naught, which is the original unshifted frequency. Times velocity plus or minus VO divided by velocity minus or plus Vs. Now sometimes in the textbook, they'll have you do it in two different steps, but I think it can get a little more complicated that way because then you have to use the output from the first and then plug out in as the input for the second, and it's easy to get them mixed up. And so here, we use this combination equation. V is the velocity of sound. Okay, and so remember that it was an increase in velocity when the observer was moving toward or away from the source. That was a numerator effect. Frequency was equal to times wavelength was velocity, and the wavelength stayed the same. So when the velocity went up, the frequency went up. So here, this is going to be V plus VO for motion toward, or V minus VO for motion away. And that's true for both the numerator and denominator expression. Now the denominator expression has to do the moving source. Remember, in the moving source, it was the frequency equals the velocity, which stays constant, divided by the change in the wavelength. And that change in the wavelength had to do with how far the object can move in a certain amount of time. And so this denominator effect then involves the velocity of the source. So VO is the velocity of the observer. And VS is the velocity of the source. And so if you use the minus sign, that's for relative motion toward. So this is if the source is moving toward the observer. So that's going to increase the Doppler frequency by decreasing the denominator. Just like here, when we decreased the denominator, when this went down, the frequency went up. And so we could decrease the denominator to make F go up. Or if we increase it, that's due to relative motion away. That's a longer wavelength. And that effect goes in the bottom. Okay, so with this equation, let's see if we can do a couple of problems. Question?
Does this Doppler effect apply to electromagnetic waves?
Yes, it's a little different though with electromagnetic waves. We'll look at that next time. I probably won't have time to look at that today. The electromagnetic waves, the velocity of light is always the same, regardless of how fast you're moving toward the light beam. So you don't have a case 1 situation. And so that changes the math a little bit. You end up with some square roots in here when you do it for light. It's different for sound than it is for light because it's not intuitive, but no matter how fast you move near a light beam, it's always moving toward or away from you at the speed of light. The speed of the source of the light beam doesn't affect the speed of the light beam itself. And so that's the basis for relativity, is that weird thing happening is why we have length contraction, time dilation, mass increases, E equals mc squared. That all comes from the fact that the speed of light doesn't depend on the speed of the source of the light, or how fast you're moving relative to the light beam. It's always going to be measured as the speed of light. Okay, so here, let's say that we have a siren, ambulance flying along at 30 meters per second with a frequency of 1,000 hertz. And let's say on this day, the velocity of sound is 340 meters per second. Now, I might give you a slightly different velocity of sound depending on the problem. And remember, that is a function of temperature. So the speed of sound isn't always exactly the same value. It looks something like square root of gamma kt over m. So it's proportional to the square root of the temperature in degrees Kelvin. And that's why sometimes we get a little bit of a variation in the speed of sound, depending on whether it's a hot or a cold day. But let's say that we have somebody that's listening here. So this is the velocity of the observer is going to be 0. But here, this is the source of the siren. And it moves toward a fixed observer at 30 meters per second. Let's find F prime. Now, who would be hearing F prime? Would it be the ambulance driver that would be hearing the F prime? What would the ambulance driver hear?
It would hear 1,000 hertz.
It would still be 1,000. Yeah, because it's relative to itself. There's no velocity of the source, and you could be in a frame of reference where it's not moving just as easily. So the velocity of the observer is, could be thought of from that reference frame as being 0. So it'd just be here times 1. F prime would equal F naught for the ambulance car. But this is F prime for the observer. Which is listening over here. Okay? And so because this thing is moving toward the observer, that's causing the waves to squeeze up a little bit in that direction. Waves will squeeze up in this direction, get more stretched out in this direction. So if you're listening from back here, it would be shifted in the other direction to a lower frequency if you were back here. But because you're out in front and the wavelength is getting smaller, we can then quickly calculate what the F prime would be. F prime would be equal to 1,000 hertz times 340 plus, and then what do we have here for velocity of the observer? 0. Plus or minus 0 divided by 340, and now it's relative motion toward, so which sign do I use?
Plus.
The top sign for motion toward. Okay, so that would be minus. Remember, we know it's relative motion toward, so you're not going to make a mistake if you say, well, how do I have to manipulate this denominator to make the number bigger? Even if you don't remember what the sign convention is, you can figure it out logically just by knowing that that's your only possibility that's going to work. Okay? And so this would be minus 30. So this would give us 1,000 times 340 over 310. So that'll give me 1,097 hertz. And you can double check that at least this is a reasonable answer by realizing that it has to be an increase in frequency because it's relative motion toward. Any questions about that example? Yeah.
So for the formula for 340 plus or minus 0 in the numerator, it would be plus 0 since it's moving toward and it's the top
Well,
side.
it's not moving at all.
Oh, okay.
So it's plus or minus 0.
Okay.
I mean, it is moving, but the observer isn't moving toward the source.
Okay. But if
So
it was,
that's what you're looking at here, is how fast is the observer moving relative to the source.
okay.
So, you know, plus 0 minus 0 would be the same thing, but it's plus or minus because it's not moving at all.
Okay, gotcha.
And so that's not relative motion toward or away. Even though it's moving toward, it's not moving toward because of this effect. And so this effect we think of as being separate from that effect.
So exactly what you were just saying is the plus and minus are individual and separate effectively from each other, independent
Yes.
from each other.
Yeah, and what you would do, and some textbooks have you do it that way, is you work one problem out if both of them are moving, if both the source and the observer are moving, and then you take that output as the input for the second calculation, which I think is easier to make a mistake with, and so that's why I'm not doing it that way.
So wouldn't there need to be some kind of position point, because doesn't the frequency constantly increase until it passes you? Is it because it's like, it's not like,
Now, as long as it has the same relative orientation, if it's passing you like this, then the components of velocity are changing. You know, as it's moving this way, you know, eventually it gets to this point, and then there's no motion at all in the direction that's toward or away.
Gotcha.
Yeah, so we're talking about when it's far enough away so that you can neglect any sideways variation.
Will we not see any problems with the velocity of the observer being other than zero because you have to do the two
Well,
computations?
we're about to do one where the velocity of the observer is not zero. Any other questions? Okay, so now, and I'm going to break you into this easily by, I'm just changing one thing at a time. What I want to do in this next example is have a stationary siren, and let's say the observer is moving toward the siren at 30 meters per second. So I'm not going to assume he can run that fast. That's about 60 miles an hour. You have to be in a car to do that. But let's do that one. You think the answers will be the same because the relative motion is the same?
Yes.
I think maybe so. But turns out that that's not quite the case. So here we'll have the velocity of the source is 0. And now we'll have this person, maybe in a rocket or something, velocity of the observer is 30 meters per second toward the source. And let's just keep that handy here. That was 1097. And what you're thinking, perhaps, is that because there's a relative velocity of 30 meters per second, that you're going to get the same answer, but you're not going to. Okay? Because in this case, it's a change in velocity, relative velocity between the two. And that's affecting the numerator term. So something here that's plus 30 is going to be different from something here that's minus 30. It's not going to be a lot different, but it is going to be a little bit different. And then we're going to need to try to understand why there's a difference. If the relative velocity is the same, you would think there shouldn't be a difference, right? Because you could always flip into one reference frame and say, okay, you're moving toward me or I'm moving toward you, so why should there be a difference if that's the case? But here, this is the velocity of the observer. The velocity of the source is 0. So for this problem then, f prime is equal to 1,000 times 340. Now it's relative motion toward for the observer, so we use the plus sign. That's going to be plus 30 divided by 340 minus or plus 0, because the velocity of the source is 0. So this is going to be 1,000 times 370 divided by 340.
It's 1088.
Thanks. So what do we have here? 1097, 1088, they're not equal. They're close, but they're not the same. Why do you suppose that is?
Relative wavelength versus relative frequency? Or relative
Well,
velocity?
one is caused by a wavelength change and one is caused by a frequency change. That's very true. And so that is the mathematically correct description. But what about physically? Why can't we say that I can just jump into a reference frame that is stationary with respect to this and then say that this is moving toward it at 30 and still get the same answer? Yeah.
Well, it depends on where the sound is emanating from is effectively the difference in where the sound is being received, because that's causing the difference in wavelength change and how that is able to sort of build up on itself. As if that is moving, it builds up on itself, whereas it doesn't effectively the other way.
Okay, I get what you're saying. Einstein's postulates, though, tell us that the laws of physics shouldn't depend on your reference frame. So that if you shift from one reference frame to another, you should get the exact same measured outcome. Can anybody come up with a physical explanation for why these two aren't equivalent to each other? If you flip from one reference frame to the other and say, okay, no, you're wrong, I'm stationary, you're moving toward me, versus, okay, I'm the other way around, moving toward me, stationary. Yeah?
The velocities are, like, relative to each other, the velocities aren't changing, but when you have the source moving, you actually have the source moving, like the sound, where the sound is coming from is moving, which is why it's different.
Okay, so what's that changing then? It's changing the velocity of sound, right? If the sound source is moving and then it produces sound, the velocity of the sound is going to be the velocity of the source plus the velocity of the sound. So if we want to flip back and forth between reference frames, we have to make a correction for what the velocity of sound is. That's why it doesn't work. That's why you have to stick with a reference frame that's fixed to the earth, because otherwise you're going to have to adjust what the speed of sound is. If you're moving at 100 meters per second toward a sound wave, then the sound wave is only moving away from you at 240 meters per second instead of 340 meters per second. So you've changed the velocity of sound. So it's just easier to stay in a reference frame where the velocity of sound is the same for each situation. All right, finally, let's look at a problem now where the siren is moving, the ambulance is moving, now it's really moving at 50 meters per second toward an observer. This is V source, this is V observer, moving away at 20 meters per second. So we still have a relative velocity of 30 meters per second between the two. But this one, this Doppler shifted frequency, as heard by the observer, is going to be different from the other two, even though the relative velocity is the same. So to do this one then, what we do is we think about, well, what is each thing doing on its own? So in other words, the source is moving toward the observer. So that means, what sign am I using down here in the bottom? Moving toward the observer. Okay. If we have it moving toward, then we use the top sign, right? So that's the negative. Good. And then what is the observer doing with respect to, and here we'll not worry about what the source is doing. Just what is the observer doing on its own relative to the fixed Earth? It's moving away. Okay. So if it's moving away, which sign do we use in the top?
The bottom sign.
The negative. So we use the negative in both of them. Because here, the source is moving toward the observer, you use the top sign, but here the observer on its own is moving away from the source, so we use the bottom sign. So that's going to be 340 minus 20 divided by 340 minus 50. So that'll be 1,000 times 320 divided by 290. 40 minus 50. Good. 1103 is it? Okay, so that's just a little bit different. We had what? 1088, 1096, and 1103. So they're all a little different from each other. they're still in the same ballpark, but they're not going to be equal to each other because of the fact that switching from one reference frame to another, like I was suggesting, would change the velocity of sound with respect to that reference frame. Okay, so that's pretty much it. There's a couple of things that I still want to talk about from chapter 17. But on Thursday, we'll go ahead and we'll start looking at light waves. Okay, so we'll be jumping all the way to chapter 33. We'll talk a little bit about electromagnetic waves, and I'll put up some stuff for you to look at. Our next quiz won't be until a week from Thursday. And the midterm will be 2 weeks from Thursday.